Hello everyone, welcome back. Myself Ayush Tripathi, working as a mentor and problem setter at GeeksforGeeks, and I welcome you all to this post-analysis video of last weekly contest 168 and talking about the problem difficulty level. So the first two problems were easy to moderate level, and the last two problems were bit complex and uses the advanced versions of dynamic programming, that is a DP with bit mask. But I have explained the complete solution of last two problems as well. So let's just start with the first problem, which is an cakewalk problem. So Geekland tax calculator, the government of the Geekland has released its a new tax policy based on annual income. As a citizen of a Geekland, you need to calculate the tax percentage you will have to pay based on your income. The tax rate as follows. So if the income is less than 3 lakh, and here the 3 lakh is exclusive, then in that case you have to return 0, that is a 0% tax. And if the income is between 3 lakh to 7 lakh, where 3 lakh is inclusive and 7 lakh is exclusive, so in that case you have to return 5, that is 5% of tax. And if the income is within this range, where the left range is inclusive and the right range is exclusive, so in that case you have to pay 10%, then 15% for this range, and 20% for this range. And if the income is greater than or equal to 15 lakh, then you have to pay 30% tax. Cool. And so in this problem, given your annual income, and you have to determine the percentage of your income you will have to pay as a tax. So this is just a cakewalk problem, and you just have to check for the multiple if condition, and if the any if condition is true, then return the percentage corresponding to that tax range. Cool. So I don't think any much explanation is required in this problem. So that's why I have directly showing you the implementation. So here the income would be given to you as a parameter, and if it is less than 3 lakh, then simply return 0. Otherwise, if it is in this range 3 to 7 lakh, where 3 lakh is inclusive and 7 lakh is exclusive, so return 5. Otherwise, if within this range, where left range is inclusive, that's why here I am having equal to sign, and the right range is exclusive, so less than sign here we have. And if that is the case, then return 10. Otherwise, correspondingly we are checking for 15 and 20, and in the else part we are returning this 30. The time complexity is constant, and the space complexity is also constant, since we have not used any extra space such as array string. Yeah, that's why time and space both are constant. All right, successfully submitted. So this is the next problem of the contest, maximum value. So in this problem, you are given an array of integers called ARR. The score of the array is defined as the minimum element in the array, and your goal is to maximize the score of the array by performing the following operation any number of times. And each operation has a 3 step. The first step to choose an element ARR of I, and the second step is to subtract k from it, and this integer k will be given to you. Then the third step, now you can add 1 to any element in the array. And the goal here is to maximize the score of the array, that is, we have to maximize the minimum element of the array by optimally performing the following operation any number of times. So let's see how we can solve this problem. So not just only in this problem, most of the such problems where you have to maximize the minimum or minimize the maximum can be solved with the help of a binary search technique. And the necessary and sufficient condition to apply binary search is a monotonic predicate function. So here monotonic means one critical point, and a predicate means the return value is boolean, either true or false. And if the problem is having monotonic predicate nature, then you can simply apply binary search, and by finding the value of low and high, that is the value of range. So let's say the value of n, that is the number of elements, it is equal to 5, and the best state which has the maximum minimum element. So let me write the elements in general form, not writing the real life values, real life examples. So let's say the elements are a1, a2, a3, a4, and a5. That is, this is the best state, and the minimum element of this array is the maximum minimum that we can achieve. And let's say this minimum element of this array a, it is equal to x, and let's say it is equal to a2. That is, a2 is the minimum element, and it could be anything. I'm just taking the arbitrary example. So a2. Now, if this is your minimum element, this is your maximum minimum that you can achieve. So if x is the best answer that I can achieve, then we cannot achieve something which is greater than x. We cannot make this array which has the minimum element greater than x. So let's say x plus some constant c1, we cannot achieve this thing, this integer. Then x plus some constant c2, not possible. Then x plus some constant c3, and so on. Basically anything which is greater than x is not possible, because we assume that this x is the best answer. And you can achieve the value which is lesser than x, that is you can further reduce the answer. So x minus some constant, let's say c4 or c3, then you can also further reduce the answer, that is x minus some constant c4, and further reduce the answer x minus some constant c5, and so on. That is all the values which are lesser than x is possible, that is function return true, and this can be your answer. This also can be your answer, and this x can also be your answer. And since this x is the best answer, so it is not possible to achieve x plus some constant c1, x plus some constant c2, that is function should return false for these values. And isn't it a monotonic predicate nature, one critical point and the return type is boolean? So if answer is possible for given value, that is if this x can be my answer, then all the values which are lesser than the x can also be your answer. And here we have to find the critical point. And in not just only this problem, all the binary search problem, we have to find the critical point. That is, we have to find this value, this x for which the function returns true, the last value for which the function returns true. Cool. And now let me just define the ranges, that is the value of low and the value of high. So what could be the minimum answer? So this thing will be given by the range of the element, and the value of ARR is in the range from 0 to 10 power 9. So the minimum answer is 0, where all the elements are equal to 0, and in that case you don't have to perform. The best way is to do not perform any operation, and the minimum maximum value is 0 itself. Then the value of I, all the values can be up to 10 power 9. So the minimum value, the minimum maximum value. So in that case all the elements are equal to 10 power 9. So in that case also you don't have to perform any operation, and the minimum maximum value is 10 power 9 itself. So this is the minimum answer can be 0, and the maximum answer is 10 power 9. Now apply binary search logic, and that's it. That is while loop, while low is less than or equal to high, and then find the value of mid, and it is equal to low plus high by 2, low plus high by 2. And now we have to check, can this mid be my answer or not? That is, all the elements of the array must be at least m, so that we can say the minimum element is m. Cool. So for this thing, to check whether this n can be my answer or not, for this thing I will iterate over all the integers, all the elements of this array. So from I is equal to 0 to n minus 1. And what if some element which is greater than m? What if ARR of I is greater than m? That is, we need all the element at least m. And if some element which is greater than m, then we can perform some operation at the element ARR of I. That is, we can reduce while the element is greater than or equal to m. And how many times we can perform this operation? How much value we can reduce from here, from ARR of I? So every time, in every operation, we select element ARR of I and subtract k from ARR of I. So it is simply equal to. So for this thing, I will use a variable extra, and the extra operation that we can perform, and initializing this extra variable with 0. And if this element is greater than m, so I will simply add the value in my variable extra. So extra plus equal to ARR of I, all the element at least m. So ARR of I minus m, so the extra value that I have, and then dividing it by k, because in each operation we reduce the value of ARR of I by k. So these many extra operations that we can perform. And what if ARR of I is less than m? So that is, we have to increase the value of ARR of I. That is so, and in each operation we can increment the value of any index by 1. So the operation that we require, that is subtract the value of m minus ARR of I. And if I add this value in ARR of I, then the value of ARR of I would become equal to m. And finally I can say all the elements is at least m. Cool. And after this for loop, I am assuming that all the elements are greater than or equal to m, and the operation that we are required is in this variable extra. And if the operation that we required is greater than or equal to 0, the operation that we require is greater than or equal to 0, then this answer m is possible. So the function must return true. and if the function is returning true, so then we have to shrink the range, that is update the value of low with the m. And if that is not the case, that is the value of extra is less than 0, that is this answer m is not possible. It is not possible to make all the elements at least m by performing the operation. So in that case we have to update the value of high, and here the function is returning false. Cool. And if the function is returning false, then all the values which are greater than m also returns false. So you don't have to check for these values which are greater than m. So just simply update the value of range, that is previously high is pointing somewhere at here assuming, and after this just simply update the value of high with m. Cool. So yeah, this is the complete solution of a binary search. Let me show you the implementation. So here I have declared a variable L and R, and the value of L is equal to 0. The minimum answer and the maximum answer is 10 power 9. So here I have written 10 power 8, but 1 followed by 90. Cool. And then the simply binary search logic, finding the value of mid, then variable extra, and if ARR of I is greater than m, then these many operations we can perform on this variable ARR of I. That is, these many times we can reduce the ARR of I by x such that the minimum element is at least m. And if it is less, then we have to increment the value of ARR of I, and these many times we have to increment the value of ARR of I. Cool. And finally, if this extra is greater than or equal to 0, if this extra is greater than or equal to 0, then we can achieve this answer m. So update the value of L with m, otherwise R with m. Cool. And finally, I will return this value L, which will be the maximum minimum value of the array, which is possible. So let's just try to submit this solution. So successfully submitted, and the time complexity, how much time this while loop will run. So it is simply log of 10 power 9 base 2, and in each iteration we are iterating over all the elements, that is all the n elements. So the overall time complexity, it is a log of 10 power 9, the number of time while loop will run. So log of 10 power 9 base 2, and then multiplied by n, because in each iteration of the while loop we are iterating over all the elements of the array. Cool. So yeah, this is the complete solution of this problem. So the next problem is minimum remaining boys 1, and in this problem you are given the position of n boys and n girls on a 2D grid. The position are represented by a 2D array of size n cross 2, and the arrays are named as boys and girls, where boys of I, 0 represent the x coordinate of ith boy, and boys of I, 1 represent the y coordinate of ith boy, and the same goes for girls array. Girls of j, 0 represent the x coordinate of jth girl, and girls of j, 1 represent the y coordinate of the jth girl. And a girl can meet a boy and form a pair if and only if both the coordinates x and y of the boy are smaller than those of girl, and each boy can meet at most one girl, and vice versa, that is each girl can be paired up with at most one boy, and we need to return the minimum number of boys who would be unable to pair after all possible meeting. And here the value of n can be up to 15, and you can find the follow-up version of this problem in the same contest, and where the value of n exactly same problem statement, but the change in constraint, the value of n can be up to 100. So let's see how we can solve this first version of the problem. So this is an NP complete problem. NP complete problem are those problems for which so far only polynomial solution exist, and the prerequisite for this problem is a DP with bit mask. But before starting the solution of this problem, let me give you a quick overview of a DP with bit mask. So DP with bit mask is nothing but a DP on subset, and a subset can be optimized with the help of a bit masking. So DP with bit mask is a DP on subset, and this subset can be optimized with the help of bit masking. That is, each mask will represent one subset, one unique subset, and mask means hiding some information inside it. And this technique is used to convert the solution which has a factorial time complexity to an exponential time complexity solution. So it is used to convert the time complexity factorial to exponential 2 power n. And this function n factorial is growing much faster than this 2 power n function. So the value of n factorial is much greater than 2 power n. For example, n is equal to 14. 2 power 14 2 power 14, which is somewhere around 10 power 4. But the value of 14 factorial, the value of 14 factorial is somewhere around 10 power 14. So can you see the difference? The difference between n factorial and 2 power n. So let me explain you the deep insights of DP with bit mask, and then I will relate this technique with the given problem. So consider integer n 15 and its binary representation 4 times 1. So how this binary representation can be made? So it has only 4 set bits, so only 4 possibility. So from this binary representation, from this state, if we change this 0 to 1, then I would get this binary representation, the binary representation of 14. And then the second possibility corresponding to the second set bit, from this state, if I change this value, change this 0 to 1, then I would get the binary representation of 15. And then from this state, if I change the bit 0 to 1, then it is representing the binary representation, it is binary representation of 15, which is our requirement. So 4 set bits, so 4 possibilities. From this state, from this binary representation, if I change this 0 to 1, then you would get the binary representation of a 15, that is a 4 times 1. And then these are the remaining sub problem, and we can recursively solve these sub problems. So how this binary representation, which is a binary representation of 7, how this binary representation can be made? It has 3 set bits, so only 3 possibility. So the first possibility, where I will change this bit 0 in this binary representation to 1, and so that it will be converted to integer, binary representation of integer 7. Then the other set bit, other possibility corresponding to the remaining set bit. Then here, if in this binary representation I would change this 0 to 1, then I would get the binary representation of 7. And the same goes for the last set bit. From this binary representation, just simply change this 0 to 1, and you would get the binary representation of 17. What will be the time complexity if we write a recursive solution, that is the brute force solution? If we try out all the possibilities, what would be the time complexity in that case? So the brute force method is to try out all possibility. So in this case, what would be the time complexity? So the time complexity is 4. The first node has 4 children, and all these 4 node has 3 children. So 4 multiplied by 3. Then in this level, all the node has 2 children, so 3 multiplied by 2, and then 2 multiplied by 1. So the time complexity would be 4 factorial. It is nothing but a 4 factorial. 4 factorial. But we can optimize it further because there are some overlapping subproblem. Now if you observe this recursive tree carefully, then you would get that this subtree is exactly same as this one. So there is an overlapping subproblem. And we can memorize it, reduce the time complexity. So overlapping subproblem, and we all know the number of different states, that is a number of unique states. How many unique binary representation here we have in this recursive tree? Isn't it from 0 to 15? From 0 to 15. From 0 to 15. Cool. And I can write a binary in a binary form, that is 4 times 0 and 4 times 1. These are the unique state that we have. So we can memorize the answer for all these state, and in future when we require to solve the same subproblem, then instead of recursively calling the function, use the answer that you have stored, and to reduce the time complexity. So the number of unique states are just 2 power n. 2 power n unique states are there. So we have a n factorial solution. So we have n factorial solution where n is the number of bits. So let's say this n is the number of bits. Instead of saying this as 15, here I would say n is the number of bits. So the number of bits in 15 is 4. So the time complexity is 4 factorial. And if we memorize it, then it would reduce to 2 power n, that is exponential. And we have already seen the difference between the factorial function and exponential function, that how fast the factorial function are growing as compared to the exponential function. So let's just get back to the problem statement. So here in the problem statement, it is mentioned a girl can meet a boy and form a pair if and only if both x and y coordinate of the boy are smaller than those of girl, and each girl can paired up with only at most one boy. So let's just first define the state, and then we memorize the states. So what are the things that we need to keep track? So we need to keep track of the index, because we can pair a girl with at most one boy, and vice versa. one boy can be paired up with at most to one girl. So here I have defined the state in this way, that is f of I comma set, and this is a set with a few elements x, y, z, and so on. And here is the definition of the set, that is f of I comma set is representing maximum number of boys can be paired up in the subarray from 0 to I in the boys array. And if the indices x, y, z, and so on, basically the elements of the set from this girls array, already paired up. So these elements of the set are representing the indices of the girls array, which is already paired up with some boy. So this is the definition of the state. And what would be the recurrence relation? So the recurrence relation here, we try to pair this ith boy to every girl, and then we'll find the best answer, that is the maximum number of boys that we can pair up. So simply iterate over all the indices of the girls array, and then for every index check whether we can pair the ith boy with that index or not. And let's say this index is lambda. So with this index lambda, we can pair up the boy with the ith index to the girl with the index lambda. And we just only have to check one condition. To make this recursive call, and the condition is girls of lambda. Lambda is the index in the girls array, and x coordinate, that is 0, must be less than the x coordinate of ith boy. So boys of I comma 0. Cool. And we have to check for y coordinate. So girls of lambda 1, that is y coordinate of girl with the index lambda, it must be greater than y coordinate of the ith boy. So I and 1. Cool. And if these two conditions are true, then we can make this recursive call, that is we can pair the boy with the index I to the girl with the index lambda. So I would just simply add this lambda in the previous set, that is the girl with the index lambda has now paired up with some boy, so we cannot include it further. So that's why we have to keep track of this thing, that is what are the indices that we have already included. So here we have this set, and then f of I plus 1, that is take me to the next index, because each boy can be paired up with at most one girl, and then plus 1, because now we can make a pair, that is here the function is returning the maximum number of boys. So we have paired one boy to some girl, and then we call the function for all the indices in this girls array which is not the part of the set and can be paired up with the ith boy. And since our goal is to maximize the answer, so that's why I would take the maximum of all the possibility. So there is one more transition that we are left with, that is there also can be the case when we do not pair the ith boy to any girl. So we have to make one more recursive call where we do not pair the ith boy. So that is f of I plus 1, take me to the next index which is I plus 1. And since we do not pair the boy with the index I to any girl, so the set would remain as it is, x, y, z, and the remaining elements that previously we have. And we all know dp with bit mask is nothing but a dp on subset, and it is basically a subset, and the subset can be optimized with the help of bit mask. So this set, I would represent this set with the help of some integer, that is a mask. So mask means hiding some information inside it, and every mask is representing one unique subset. Cool. And what would be the base case? So the base case, if the value of I is greater than or equal to n, so let me write in this way, that is f of n comma set, let's say x, y, z, and some element. So this value is equal to 0, because we all know that is we only have n boys which are indexed from 0 to n minus 1. So if we reach out of bound, then we have to return 0. So this is a base case, and the complete explanation. And what would be the time complexity? So the possible value for this set, if there are n number of girls, then we only require 2 power n mask, and it is from 0 0 0 to 2 power n minus 1. Cool. Yeah, this is the time complexity. Or let me just explain you in this way. So let's say the value of n it is equal to 3. So what are the possible subset of this 3 we can have? So it means we can have a empty subset, empty subset, then the subset of one element, so 1, and let me write the indices. So that is index 0, index 1, and index 2. Cool. So empty subset, and then the subset of one element, so 0, then the subset of one element, basically all the subset of one element, so 0, 1, and 2, then the subset of two element, 0, 1, and 1, 2, and 0, 2. Cool. These are the subset of two element, then the subset of three element, the subset of three element, which is 0, 1, and 2. Cool. So how we can represent in terms of in terms of a bit, and if and the number of subset, it is equal to 2 power n, because for every index we have two possibilities, that is include or exclude. So that's why we only require 2 power n number of mask, and the range of this mask can be from 0 to 2 power n minus 1. From 0 to 2 power n minus 1 has a 2 power n integer. So here the value of n is equal to 3. So let me write all the integers from 0 to 2 power n, which is 2 power 3, and 2 power 3 minus 1, which is equal to 7. So all the integers from 0 to 7, and all integers are representing one unique subset. So 0, 1, 2, 3, 4, 5, 6, and 7. 2 power 3, which is 8, 8 minus 1, which is equal to 7. So the binary representation of 0, 3 times 0, and here I am writing in terms of 3 bits, then 0, 0, 1, then 0, 1, 0, and then it would be 1, 0, 1, then 1. Okay, so here it should be 0, 1, 1, 0, 1, 1, then 1, 0, 0, and 1, 0, 1, then 1, 1, 0, and finally 3 times 1. So here these bits number are representing our index. So index 0, index 1, index 2. So if the bit corresponding to the index is set, then this index is having contribution in the current subset. So here all the bits which is corresponding to the indices are 0. So it means it is representing an empty subset. So subset with no elements. Then here the bit corresponding to index 0 is set. So here it means subset with the index 0, or you can say the value at index 0, because from the indexes you can easily get the value. And this one is representing a subset with the element 1 or index 1, and this one is representing a subset of two elements 0 and 1, because here we have a bit as set at position 0 and 1. Then it is representing a subset with element 2 or index 2. Then this one is representing 0 comma 2, because here the bit corresponding to index 0 and index 2 are set, and this one is representing 1 comma 2. The bit corresponding to index 1 and the bit corresponding to index 2 are set, and the binary representation of 17, which is 3 times 1. And here all the indices are having bit set, so it is the contribution of all the indices, so 1, 0, 1, and 2, and these are the 2 power n subsets. So yeah, each integer in the range from 0 to 2 power n minus 1 representing one unique subset, and we all know these are the only unique states we have, so we further memorize it. We memorize it to reduce the time complexity, and whenever we require the answer for the same state for the same binary representation again, then instead of computing that answer again, I would simply return the stored answer. So this was the complete explanation from my end, and now let me just show you the implementation. So this is the function which is given to you, and we have to complete this function where it has a parameter n, number of girls and the number of boys, and the number of girls and number of boys are equal. Then here a vector, 2D vector of n cross 2, size n cross 2, which is representing the coordinates of boys. Then another 2D vector of size n cross 2 representing the coordinate of girls. Then here I have created a DP array of size n, and then 2 power n plus 1, and you don't have to write plus 1 because the mask value is from 0 to 2 power n minus 1. So these many unique indices we need, and here we have n because the possible value for this index I. So the possible value for this index I is from 0 to n. So that's why 0 to n minus 1. So that's why the size would be n, and here in this case the possible value for set in terms of bit is from 0 to 2 power n minus 1. So I can say 2 power n, and in the range from, we need an index in the range from 0 to 2 power n, same as the requirement, and both the ranges are inclusive. Then here I have called the function for 0 comma 0 and here this 0 is a index in a boys array, and this 0 is a current mask, which is representing empty subset, because so far we did not pair any girl to any boy. Then this boys array and girls array, then n, the number of boys and the number of girls we have, and simply this is a DP vector for a memorization purpose. And here I have set all the values to the -1, and this function would return me the maximum number of boys that can be paired up in the subarray from 0 to n-1. And so I can simply subtract this value from n, so that we would get the minimum number of boys which cannot be paired up. And yeah, here we have our function. So this would be our base case. If the index is greater than or equal to n, that is v reaches out of bounds, so simply return 0, because now you cannot pair any boy. And then here we have a memorization condition. If I already know the answer for this state, that is dp of index comma bit mask, and if it is not equal to -1, then return the answer of this state, do not compute it again. And then x coordinate of the ith boy and y coordinate of the ith boy. Then here I am calling this function for exclusion part, because there is also a possibility where we do not include the boy of the current index. So in that case, take me to the next index, and the bit mask, that is a set, would remain as it is, and the remaining parameters. And the other transitions, that is I would iterate over all the indices of the girls array, and if the current index in the girls array is already part of the set, is already set in the bit in the mask, then I would simply continue, because we can pair the girl with at most one boy. So if this index has been already paired up, then just simply skip this iteration. Otherwise, I would check the coordinate. I would check the coordinate of the girls array for the current index, whether we can pair the current index with the boy or not. And if that is the case, here I'm just simply checking the coordinate. Then I would make this bit as set. This bit as set, because basically I am including the ith bit. I am including the bit in the set, and then I would make a recursive call and take me to the next index. Then this is a new configuration of mask, and then the remaining parameters, and maximum of answer that we have so far, and 1 plus this recursive call. And this is a backtracking step, that is before pairing the boy to the other index, we have to make this index unset. That is we have to remove this index from the set. So that's why here I'm using an XOR operation, and 1 XOR 1, which is equal to 0. So here I am simply here in this bit in this variable bit, the ith bit is set. So here if I take XOR with 1 left shift I, then it means 1 XOR 1, which is equal to 0. So I am simply making this bit unset, and finally I will return this best answer, maximum answer. And first of all I will store it, and then I would return it. So let me just try to submit it. So successfully submitted. And the time complexity is the number of different states. So n possibilities for index, and 2 power n number of masks we have. So yeah, this is the complete solution for the first version of the problem. So the next problem is minimum remaining boys 2, and this is the follow-up version of the last problem. Here the value of n can be up to 100, and this is a constructive problem where you have to design your own algorithm along with the proof. And there are multiple methods to solve this problem, and the one method that I have used here is to visualize this girls and boys array as a graph where each index is represented as a node. So let me just explain you the algorithm, and along with the example. So consider the value of n is equal to 3, that is 3 girls and 3 boys, and these are the coordinates of girl 5, 5, 4, 4, and 1, 1. Then these are the coordinates 10, 10, 3, 3, and 4, 4 as the coordinates of boys. So let's just see what are the indices of the girls which can be mapped with the indices, with some indices of this boys array. So let me write the indices as well. So index 0, index 1, and index 2. So a girl with the index 0 and coordinate 5, 5 can be paired up with the boy with the index 1 and coordinate 3, 3, and this girl can also be paired up with the index 2, boy with the index 2 or coordinate 4, 4. Then the next girl, which is with the index 1, can be paired up with the boy with index 1 and coordinate 3, 3, as here we just only have to check one condition, That is, the coordinates, the x and y coordinates of the girl must be greater than x and y coordinates of the boy, so that we can pair them together. Now let me just quickly draw a graph corresponding to it. So I am using a red color pen for this girls array, and a green color pen for this boys array. That is, all the node which are colored green is representing the index of a boys array, and the nodes which are colored red representing the index of a girls array. So index 0, then index 1, and index 2. Cool. And then indexes of a boys array 0, 1, and 2. So the girl with the index 0 can be paired up with the boy with the index 1, and boy with the index 2. So these are the two edges, and the girl with the index 1 can be paired up with the boy with index 1, and girl with index 2, which has coordinate 1 comma 1, cannot be paired up with any boy. And you don't have to use two colors, red and green. Just simply merge these two maps, these two indices together. And what I'm trying to say, you don't have to create a two graph, just simply merge them together. So node 0, and there is an edge from 0 to 1, and there is an edge from 0 to 2, and then there is an edge from 1 to 1. Cool. Yeah, so this is an underlying structure of the graph. Here all the outgoing edges are representing that current index in the girls array can be paired up with the outgoing edges, and here incoming edges are representing that there is an girl which can be paired up with the boy with the current index. Cool. So let me just quickly draw this graph. So 0, and there is an edge from 0 to 1, and there is a self loop 1 to 1, and then there is an edge from 0 to 2. So initially we do not know that which pair we have to form. We have to which index of this boys array we have to select, and we map that index with the index 0 of the girls array. Initially we do not know this thing. So what I will do, I will try out all the possibilities with the help of a DFS function, and here I will use one array. Let's say array matched, and here I will matched of u. In matched of u, I will store the index of the girls array to which I have matched index u of the boys array. So starting, let's say we started a DFS call with the index 0. So DFS of 0. So here what I got an edge from 0 to 1. So what I will do, I will simply check whether this index 1 has been matched or not, and this index 1 has not been matched with any girl so far. So what I will do, I will simply match this index 1 of the boys array with the index 0 of the girls array. So here I will simply say matched of 1, which is equal to 0. Cool. And every index, basically for every index I just wanted to map the index to any index of the boys, any index of the boys array. That is, we just wanted to relax an edge. So here I will simply return back from the recursive call. So I will simply map this 0 with the index 1. That is, 0 is corresponding to the index of girls array, and 1 is corresponding to the index of boys array. So I will simply map these two together, and then I will call the DFS function for the next index. So the next index is 1. Cool. And so DFS of 1. And what are the neighbors or the edges, outgoing edges of 1? So here DFS of 1, and 1 has only one edge to itself. So what I can see here, the girl with the index 1 can be mapped with the boy with the index 1. But this index 1 has already been mapped with some other index, and that other index is 0. So what I will do, I will simply try to relax this and make a call for DFS of 0. So what I'm trying to say, so here matched of 1, which is not equal to -1. So first of all I will set all the values to the -1. And if it is -1, then this means current index has not been matched with any other index. So if it is not equal to -1, then it means it has been already matched. So matched of 1, there is an edge from 1 to 1, and matched of 1 not equal to -1. This means index 1 has been matched with some other index. So in that case, what I will do, I will simply make a call. to the matched of 1. And instead of writing in this way, I will write in this way, matched of 1. So what I'm trying to say, I will map boys of boys of 1 to the girls of 1. I will map these two indices together, girls of 1, and then I will make a recursive call to the node which was previously at the place of matched of 1. So what I'm trying to say, in the previous case, boys of 1 has been matched with girls of 0. Index 1 has been matched with index 0 of this girls array. So now once I get this edge, that is 1, there is an edge from 1 to 1. So I will simply update this mapping and make a call to index 0. That is I will simply say to index 0, instead of this matching, check for some other node, for a mapping, because this node 1, I will map this node 1 with itself. Cool. So matched of 1, which is nothing but 0, matched of 1, which is nothing but 0. And then here what I will see, DFS of 0. This is nothing but simply DFS of 0. And from DFS of 0, what I can see here, this 1, which is already visited,